I would have liked to welcome you since this is our building, but I was stuck for 48 hours in the airport. So that's another reason to ask questions, to give energy to this talk, so please. Also, I could not come to the previous talk, so if some parts are too redundant, just please, let me know, and I would accelerate. And if it's too fast, then. Okay, elementary excitation in amorphous materials. I think, define what I mean by this later on. And there is some kind of structure. So what I would like to do first is to introduce some question about disordered solid amorphous materials that I think are of interest for this group. And then discuss a sort of conceptual framework to think about those questions. And that's really based on this elementary excitation and this notion of stability and marginal stability. And then I want to give two examples to this framework. One where you think about continuous excitation, by which I mean, in that case, soft elastic modes. And then I will conclude the talk by thinking about discrete excitation. All right. All right, so as you know, many materials around us are actually not crystalline, they are amorphous, so that's one reason to think about them. And in this talk, I will be discussing, in some sense, three cases. So one case are granular materials. So in this case, the particles are hard, so you can think of them as being essentially not deformable. So it's more a problem of geometry. And they are big enough so that temperature does not actually play a role. So another system of interest is, again, when temperature can be neglected, but when particles are soft. So an example is, that's for example what you eat is often like that, a mayonnaise. So if you zoom in a mayonnaise, you find that those are droplets that are pushed on each other. And so in those systems, particles are actually deformed. And then I will also be discussing the cases where temperature is actually relevant, and I will discuss more the specific case of colloidal glasses. So in all those systems, there are long-standing questions having to do with the solid behavior, which I will review some of those questions. The liquid, and maybe one of the most vexing problems is actually the transition between the solid and the liquid, the jamming transition. Although this name jamming transition I think is a bit dangerous because the transition from liquid to solid in those different cases I think is actually very different. There are some commonalities, but I think it's important to emphasize differences too. All right. Okay, so let me talk a little bit about the solid. So imagine you have droplet interacting. So for droplet of oil into water, you can think essentially as some kind of harmonic repulsion between particles if they touch, and they don't interact if they don't touch. So maybe the first question you can ask is about the linear stability of a system like that. So if you have a system of interacting drop, clearly what you must have is that forces are balanced. That's one first constraint. Another constraint is that you must be at a minimum of mechanical energy. That means that the Hessian, so that's essentially the matrix of second derivative, must be positive definite. Okay, so that's my notation. That's delta R here would be a displacement field, so its dimension is n, the number of particles, times d, the spatial dimension. And the Hessian is a nd times nd matrix. So I think Andrea discussed that, but I will come back to this. Actually, the fact that requiring that the Hessian is positive definite is actually already a non-trivial constraint on those systems. Okay, so now let me introduce the concept of vibrational modes. So if you impose an external force field on the system, you will move the particles, and the linear relationship between the two is precisely given by this Hessian H. And so H contains all the linear response of the system. And in particular, it contains the vibrational mode of the system. So, for example, if you have a system where you have no damping, which is inertial, you get just from Newton's law that the mass times the acceleration is the force, and you can actually diagonalize H. So my notation, lambda would be the eigenvalues, delta R lambda would be eigenvectors. And you see that along those eigenvectors, the dynamic is just that of an harmonic oscillator whose frequency omega is related to lambda in that way. All right, so one important quantity is the spectrum of H. I mean, often instead of thinking about lambda, we think about frequency, so d omega. And that's a quantity that you can measure. And maybe I should start by discussing something that you probably, all of you know, which is how does this behave, say, in a crystal? So in a crystal at low frequency, you would have plane waves. So you would have a linear relationship between frequency and wave vector. So counting the density of state is like counting wave vectors. And as you remember for solid state physics, in d dimension, the number of wave vector k whose magnitude is k goes like the surface of a sphere. So it goes like k to the d minus 1. So that leads us to the Debye result. For example, that in 3 dimensions, if you have a crystal, the density of state grows quadratically. Okay, so this, I'm sure Andrea told you about this, but okay. So that's for a crystal. If you look at glasses, you find something different. You find that glasses compared to crystalline counterpart tend to have more soft elastic mode in them. So one way to look at this is to plot the density of vibrational mode divided by omega squared. That should be just a straight line for a crystal. And what you find in glasses is that this has a hump. And this hump, it's a fancy word, but it's called the boson peak. If you look at, so you have an excess of soft elastic mode in the system. If you look at mode in this frequency range, you find that they are heterogeneous, unlike plane waves, but they can be extended. So one long-standing question is, what is the nature of those objects, of those modes? Okay, so okay, I think this again. I was told you heard about this. So if you want, you can also characterize those modes. So the density of state would affect thermodynamic properties like the specific heat and so on. But you also have observables that characterize really the eigenvectors themselves. And one is the diffusivity. So the diffusivity di omega has to do with the following experiment. So imagine you have a system. You take one particle, this particle in red, and you start to shake it at one given frequency, omega. If you do that, you will start to put energy in your system. And on long time, this energy is going to be diffusive. Right? That would behave like a Gaussian. So what you can define is a diffusion constant that enters in this relationship. R goes like the square root of this diffusion constant times the time. So if you could do an experiment like that, you could measure a diffusion constant at a given frequency omega, and that's what's called the diffusivity. Okay, so what should be the diffusivity? If you had a classical system at low frequency, what you do get actually, is Rayleigh scattering. So you can think about a wave and perturbation theory on the scattering of a wave. What you find is that the diffusivity would, the scattering length would go like 1 over omega 4. That's the same term that you learn when you think about why the sky is blue, for example. So in a disordered elastic system at low frequency, you would expect to have that. And actually, there are experiment and data showing that you have that. But if you go to higher frequency, if you go, for example, where you start to have those excess soft mode, then you find that the diffusivity seems to be flat. So all this, you heard this before, right? I'm just repeating essentially. Okay, so just tell me also if you if this was done. Right. So those are different observables to explain in some sense. Another one that was studied a lot, especially in the context of granular materials, is the sort of green function of the problem, the elastic response to a point strain. So those are the beautiful experiments done in the group of Behringer, where you have photoelastic disks, and you send polarized light through the system, so you can actually see which particle carries some stress. So initially, this should be all blue, but then this experimentalist is imposing a strain on the system. And then you see that the system responds with those in a very heterogeneous way, and you have those so-called force chains. And so again, one question is, what is the statistics of those force chains? Is there a characteristic length scale associated to them, and so on? All right, so those are aspects of amorphous solids related to their linear response. And so I'm still in the solid. Here you have a way to, I'm going to discuss a particular case where I'm sure Andrea again talked about this, but it's of special interest because I would say all the properties I told you, if you were looking at a typical glass, the sort of length scale that you would get maybe for those force chain would be 10 or something like that, 10 particles or something like this. And you can come up with many theories to explain a number like 10. So this system, which is made of just simple packing of frictionless spheres, was very useful because in this system, all those properties I told you about, these boson peaks, those length scale. So once you have a system like that, you can really test theories in a stringent way. But again, I feel I'm repeating what Andrea said, but so essentially you look at purely repulsive particles as a function of packing fraction. If you prepare the system, for example, by a very fast quench and you decompress, you get amorphous configurations. And as you change the packing fraction, at some point the pressure vanishes. And if you go even to smaller packing fractions, there is no more mechanical energy in the system. This phi j is preparation dependent, but that's not really important for what I'm going to discuss. The key point is that as you approach this point, all those properties I started to discuss, linear response in those disordered materials, show scaling. So for example, if you go right very close to this point and you look at the density of vibrational modes, instead of being quadratic like you would expect from the BI, it's actually flat. So that means that at very low frequencies, or even at very large length scales, the system never behaves like a continuous elastic solid. So the system here was, for example, harmonic, half harmonic interaction potential. And then again, you heard about that, the fact that as you approach this point, those properties show scaling. You have scaling in the microscopic structure. For example, if you look at the coordination, it has a finite value at jamming, but then if you compress, it grows like the square root of the increased density. Here, this is just twice the spatial dimension. But you also have scaling in vibrational properties. So for example, if you look at this density of vibrational modes, you see that as you increase the packing fraction, so this was at the critical point here, you enter more and more in the solid phase, you see that you reach this plateau at a characteristic frequency that grows with compression. And you can define this frequency and you show that it's scaled like the excess coordination. So those data were very appealing because they show giant behavior and scaling, and so you can try to go after them. All right, so now you can also think about essentially everything I told you in the introduction. You can look at it in this system. And one aspect you can look at is, again, this sort of green function, the response to, for example, a dipole. And you see that if you have a system which is at large density, in fact, this is a spring network at large coordination, but that's very similar. You see that the response to a dipole looks pretty similar to what you would get in a continuous elastic solid. But if you approach this jamming transition, then you have an entire region which is very heterogeneous. And this region diverges in scale, and there was a bit of debate about what is this scale, but we redone numerics because we had a prediction, and we think this goes actually behaves like this. So it's just a very convenient system to test ideas about elasticity in amorphous solids. Okay, so that was the solid. Those were properties of the solid. One I didn't discuss, but I will come back to it in the second part of the talk, is plasticity. So I was talking mostly about linear response, but I will go back to plasticity. But here I want to immediately go into the liquid and think about how you have a liquid-solid transition in the system. It's a transition which there is no change of symmetry. It's very different from liquid becoming water becoming ice, but you have key changes in the dynamics. Now I want to discuss what I think are two very different jamming transitions. But they can be illustrated in this phase diagram. So again, I'm looking at this very simple system of repulsive particles like that. And so far, I just discussed this line. And I had no stress on the system. Now you can put some stress on the system and drive it at the strain rate gamma dot. Okay? So as gamma dot increases, it means that the shear stress also increases. So there are two different phenomena that can happen. One is if you're very close to this line here. So in this region, the strain rate is small. It means that the stress is small. It means that the particles are essentially not deformed. So you can think about really hard particles. So that models, say, a dense granular flow. So that's this region. And as you increase the packing fraction, as we will see, at some point, it becomes solid at that point. There's another way to have a liquid-solid transition is if you're there in the phase diagram. So for example, a mayonnaise, if you push on it strongly enough, it would start flowing. So the strain rate tells you how fast it flows, and you can decrease the strain rate, and at some point, at that point, you become solid. And this, I will refer to it as yielding transition. Mayonnaise has a yield stress. At this point, the stress will have a finite value. If you go past this stress, it actually flows. Yes?
Sorry, so what you are now calling jamming of hard spheres is that you put an infinitesimal, you put a small gamma dot.
Yeah.
That's infinitesimal, but not zero.
Yes.
Then you compress and then you...
Yeah, it's a limit where you're not exactly at zero, you're just above it, yes.
And then in that case, this phi c is not anymore...
Yeah, so I will comment, then it's well-defined.
This is a well-defined.
Then it's a well-defined quantity, yeah.
While if the one you were doing before is strictly gamma dot equal to zero. So
right, exactly.
One is protocol dependent.
Exactly,
okay.
Exactly, right. So maybe...
No.
Yeah, well, actually, no, but I was planning to mention this discussion here. So, indeed, so let me start from thinking about that. So it's essentially the physics of dense granular flows, and you can have. So one way to do it experimentally is you take a layer of sand and you tilt the system. If you tilt it with a large angle, it would flow fast, and the density would be small. But as you lower the angle, the density becomes larger and larger, and at some point, boom, it stops. The packing fraction at which it stops is actually well-defined, and in the field, it's called the critical state. So essentially, that's because you reach a stationary state. So that if you take a granular material and you shear it quasi-statically for a very long time, the packing fraction may have some transient behavior and you have dilatancy and so on, but eventually it would reach a stationary state. That's called the critical state, and that's a well-defined number. All right, so now what's the physics as you lower this angle and you approach the solid phase? You have a problem of crowding, so the system is denser. And one question you can ask is how can particle rearrange in a very dense environment? And actually that's something that you can sort of easily observe experimentally. So that's what's done by Pouliquin. You just do that. You have this layer of sand and you decrease the angle. And what you do is that you take a video from the top and you look at the velocity field of the particles. And you hear those pictures, you remove the mean velocity and you just look at the fluctuations of velocity. And what you find is that if the slope is high and you go fast and it's dilute, essentially the fluctuation of velocities are very small. But as you approach this point, suddenly the dynamics starts to become very collective. So when it's too dense, particles cannot decide on their own where they want to go. They need to coordinate, if you want. So you see some kind of big eddies that appear in the flow. And so one question is, what is this length scale? What governs it? Right, I like to show this movie because I think it gives you an intuitive picture of what's going on. So this is, when you think about dense granular flows, you can think of them in air, where inertia is very important, but you can also think of them in a viscous liquid. Then it's called a suspension. And here it's an example of non-Brownian suspension. So if the particles are big enough, Brownian motion is not relevant. And then inertia is not important. And in that case, you also see that you have a growing length scale in the system. So what you will see here are movies of systems that are identical, except that the packing fraction is very slightly different. Here, it's just a bit a lower packing fraction than there. It's the same strain rate, so you're changing the shape of the box at the same speed. And what you see in black here are the forces between particles.
There is viscosity in the...
Exactly. So it's over-damped dynamics.
Okay, in that sense, what you mean by non-Brownian?
Yeah. No. So that's another issue. So it's non-Brownian, but even when temperature is negligible, it could be inertial or inertia could play a role or not, depending on the Reynolds number in the. So this is a situation where you really kill out. The viscosity is large enough so that you don't have inertial effect. In a real suspension, you would, as a function of strain rate, you will, at small enough strain rate, you would be like that, and then at some point you would have a transition to an inertial regime, where it would look more like a granular flow in air.
And you don't have hydrodynamic interactions; you just have.
Yes, so that's a very simple model. Yeah. For those who know, it's similar to this Olson and Title model. So. Okay, so I didn't show you the movie yet even, but okay, so here the interactions, so you have hardcore repulsion, and in this model you think about, it's a very simple model where you think about the underlying fluid as being unperturbed by the particles, and one particle wants to follow the sort of frame of the fluid. If it does not, then it gets a drag. But it turned out that this simple model, you could do a more realistic model where you would have drag in terms of it's believed that what dominates dissipation are lubrification forces between particles. So if you put a drag that has to do with relative motion of particles, you get the same scalings as far as the jamming transition is concerned. Numerically, that seems to be the case, and theoretically, we think it should be the case too. Okay, but let me show you the movie. So, right. So what you're supposed to see here is that a very small change of packing fraction changes a lot the dynamics that here it's very smooth and not very collective. But if you look in this movie, it seems as if locally the particles were on a small scale sort of already jammed and moving as blocks. That's a very qualitative statement, but you could get it by looking at velocity correlation, and you would see a growing length scale here. So another point that I want to make is that clearly this problem has nothing to do with percolation, because even here, when you're here and here, you're not jammed, and you still have a percolated network of contact. What you can do is those numerics are in experiments, and it has been done by many authors, is to also look at rheological properties, not just kinetic, but also how for example, a suspension has an overall viscosity. You have the viscosity of the solvent, but when you add more and more particles, the viscosity grows. And in fact, here it's going to diverge as you approach jamming, and it diverges with some non-trivial exponent. Okay, so the point is that this case, dense granular flows, seem to behave like a continuous critical point, where you have a diverging length scale and a non-trivial exponent characterizing, for example, rheological properties. Okay, so that's fast. Let me now talk about the other situation. And this I will discuss it a bit more at the end of the talk, but that's when you have compressed a system of like a compressed particle like that, and you start shearing it. So now particles are deformable. And as you lower the stress, you're going to lower the strain rate, and at some critical yield stress, the strain rate goes to 0 when you're here. It seems that this approach is again a phase transition, and it appears by several observables. So one that you can look at is the stress-strain rate relationship. And you see that the flow curve is singular when sigma goes to sigma c. So the relationship between strain rate and my sigma is a stress. So that's how much you increase the stress on the system. That's how fast you flow. There seems to be a singular relationship between those two. Another way to see that you have sort of critical phenomenon is to put a boundary. If you have a wall, for example, and you go to stresses that are close to sigma c, then you can measure on which length scale the wall has some effect on the flow. It's called non-local effects. And non-local effects seems to have a growing, diverging length scale as you approach this sigma c. Something else which is interesting is that if you're right at sigma c or slight or below, you see that, so you're in the solid and you drive it, you see plasticity, you drive it quasi-statically, you see avalanche type response. Sometimes you have small rearrangement, and sometimes you have very big ones. But this I will come back to that. Okay, so I think those systems were driven system at 0 temperature. Now you can think about a thermal system. That's a glass transition. And here I just want to introduce it in the case of a colloidal glass. So you have hard particles, and they are bouncing into each other. And what you change then is the packing fraction. And what you find is that at low packing fraction, okay, there is some relaxation time tau. If you want, you can think of a particle as being surrounded by neighbors, and it's a characteristic time by which a particle can escape from its cage. And what you would see at low packing fraction is that this is a small times, but as you increase the packing fraction, suddenly this time shoots up. And at some point it becomes so large that on experimental time scale you cannot equilibrate the system, you have a glass. So on your time scale it behaves like a solid. But if you look, what that sort of surprising aspect of the glass transition is that if you look at the particles, in the structure nothing much seems to have changed. They were rattling around here and here, and you change a little bit the packing fraction, but the reaction time changed a lot. So you have some kind of emergence of rigidity. You had a fluid, and here you really have a solid. And so one question is, how do you how do you think about that? How do you think about those particles bouncing into each other, suddenly forming a structure that allow them to carry a stress? And once they do, you can ask, what are the properties of this solid phase, this colloidal glass? And one aspect I want to discuss is the sort of little dents that the particle do there. So, right, so you have a solid, but it's still thermal, so the particles are going to move around. And one question is it that this microscopic dynamics that takes place here, these little dents of the particles, does it actually reflect the mechanism by which rigidity is acquired? Okay, so that's a point I want to discuss too. Okay, so those were the sort of questions, themes I want to discuss. And now let me tell you one of the reasons why it's challenging, in my view. So for example, if you think about granular flows. So a lot of work has tried to think about granular flows as a perturbation around the gas, the dilute system, where you have binary collision. But this is going to fail completely when you have the sort of collective, you have network of contact and you have those length scales that appear in the system. Then it's by nature completely collective. And thinking about binary collision, I think it would lead you nowhere. So instead of thinking about a perturbation around the dilute limit, what we've been trying to do is to think about a perturbation around the solid. But then you have to think about really the solid phase. And one difficulty in all those systems is that the solid is glassy. It's an out of equilibrium structure. And in those glassy systems, you have the sort of this sampling problem, right? So if you think about a pile of sand, that would not be energy, but maybe volume. You have an exponentially large number of states that are possible, of metastable states, right? And if you want to do a statistical description of this problem, you would like to know with which probability different states are visited. But in principle, you're not allowed to use thermodynamics because the system is out of equilibrium. So one approach, for example, in the field of granular materials has been to use thermodynamics anyway. To say, well, the metastable state at the same volume, I will assume that they are equally likely visited. Essentially an approximation like this. Okay, so here we're going to try to do something different. Okay, so that's the framework. Okay, so we're going to start from the solid and think about some kind of perturbation around the solid. And one first concept that's, I think, very important, which had been historically very important in other fields, also glasses in physics, for example, Coulomb glasses, but for some reason didn't really impact amorphous materials, although I think it's very important. So it's this concept of elementary excitation. So what is that? So you think about those are the sort of minimal rearrangement, collective rearrangement of the particles that you find if you drive the system. This idea, I will then sort of give you several examples of excitation in different situations. So it will become clearer. So the first aspect is to seek to identify what are those elementary, this minimal rearrangement that the system can do. And then the second idea is once you identify them, you think about the stability of the solid. And you think of, if the system is solid, it means that those excitation must be stable in some sense that I will discuss. And that ends up constraining the structure, that ends up constraining the sort of structures that you can visit, and also constraining the density of excitations themselves. All right, so that you identify those objects, you require that those excitations are stable, that constrains the structure of the system and the density of excitation. Once you have the density of excitation, then you can seek to build a description of the liquid phase, or of the plasticity of the solid, or of elasticity. And here, in this presentation, I want to talk about 3 different kind of excitations. Okay. All right, so again, so the notion of stability is going to be very important. There will be 2 kinds of stabilities discussed in the talk. So one is linear stability. It's just the fact that you have to live close to a minimum. You cannot live close to a saddle if you're in a 0 temperature system. And this stability will be important when we discuss this anomalous mode, the soft elastic mode I told you about. But then there is another kind of stability that's important, some kind of nonlinear stability. It's a requirement that the system does not live, most likely does not live close to a giant cliff. That is, a very small perturbation cannot extensively rearrange the system. And this, we'll see, is also constraining. All right, so essentially, we'll describe excitation, think about stability, and what you end up at the end is a sort of phase diagram. So here the axes are not prescribed, but they can be in particular aspect of the structure of the material. And we will get a phase diagram with some line and that separates jam configuration, which are stable, from unstable configurations. Then what we'll find is that sometimes it can be argued or even proven that the system is not going to lie anywhere. If you have a solid, it's not going to lie anywhere in this stable region. It's going to lie specifically on this red line. And this is what I would refer to as marginal stability. And actually, it's important for 2 reasons. One is that it can solve this sampling problem. It tells you that instead of living on this anterior plane, you live on a line. So it reduces the state that you actually visit. Sometimes it's all you need to know to build your theory. Sometimes it's not enough. Sometimes it's all you need to know. Another interesting aspect is that on this line, the density of excitation is actually fixed. So if you know that you live there, you have access to it. All right, this was abstract. And now let me talk about examples. So the first example, I will start by continuous excitation. Continuous in this, I will be talking about the soft elastic modes. We call them anomalous modes that I introduced for packings. Continuous in the sense that it's an elastic mode, so I can continuously change the amplitude against it, along it. So some ideas I will review, and this is where probably my talk again overlap a bit with Andrea's talk, is that those kind of objects, which we think are very important if you want to think about transport or force propagation, are affected by some aspect of the structure, in particular by the sort of measure of how your glass is connected in packing the coordination, and also by pressure. So this I will review. Obviously, the density of this object, in this case, it just appears in the density of vibrational modes. And I will discuss the fact that those objects are important to think about this unjamming transition. So when you reduce the packing fraction towards this phi j, are important if you want to think about colloidal glasses. So those 2 cases I will discuss. We think that they're also very important to think about this movie I showed you about the suspension and the particles moving around. We think that the motion of the particles is in fact, so in this case, you were not a solid. Remember, you have those hard particles forming this sort of contact network. It could flow. But still, we think that the geometry of this flow is closely related to this kind of object. But I will not review that. That's discussed in those papers. And I will discuss the fact that those modes can be marginal in some conditions. All right, so now I just want to give you a sense of why those objects, those soft elastic modes, are strongly dependent on coordination and pressure. And I would just, actually in this entire talk, I will not do almost any theory. I just want to give some intuition of what's going on. And here, I'm just reviewing some idea of Maxwell. We're thinking about the stability of engineering structure. And he told us that if you have, for example, a network of points connected by springs, look at this one, for example. This one is mechanically stable. You cannot deform it for free, apart from translation and rotation. But if you remove this link, then this system is floppy. It has a zero mode. So Maxwell was interested in the stability of this engineering structure, and he said, if you want the system to be stable, you must forbid, you cannot have floppy modes like that in the system. So when do they appear? Well, then you can think about what equations are satisfied by those modes. So those modes, they have to keep all the springs. They cannot change the length of those springs. So that's this equation here. It's not really important to follow it, but Nij is just the unit vector along the spring ij. This is just saying that the relative displacement in each spring has to be orthogonal to the direction of the spring, right? Otherwise, you would change the length. So it's a linear constraint, and you have a set of linear constraints for every spring you have. And so Maxwell said, well, I don't want to have a non-trivial solution to this problem. So it's a linear system. I must have more constraints than I have degrees of freedom. Number of constraints is the number of springs, and number of degrees of freedom is n times the spatial dimension. So that tells you that the coordination, so if you want to be stable, you must have more constraints than degrees of freedom, and C must be larger than ND. You get something like V has to be larger than twice the spatial dimension, okay? So coordination is very important. If you're not coordinated enough, you will always have some zero mode in the system. As you approach this, when you unjam those packings, actually they approach this critical value for the coordination. If you are even going to lower coordination, actually that's what happened in this movie, where you're not enough coordinated, then you have zero modes, then you have floppy modes. Actually in the movie of the suspension I showed you, the displacement is along floppy modes. So the point is that floppy modes appear when the coordination is below some threshold. I think it's very intuitive, and I would not derive it, that if the coordination is above, you will have a reminiscence of the proximity to this, of this threshold in the spectrum of modes. Okay, so coordination certainly matters. Another aspect that matters, and again I think it's very intuitive, is the pressure on the system, and this you know it in elasticity, right? That if you take thin objects and you, for example, push on them, it can lead to instabilities like buckling for a thin rod or a thin membrane. If you pull on them, it's the opposite, like the string of a guitar. You're increasing frequencies in the system. And at a microscopic level, you can think of it very simply where this term comes from. So here I'm thinking about a spring, but you can think about an interaction between those two particles. So you just have to write, imagine you have a spring here, its stiffness is K, its length is R, and you ask what is the change of energy compared to some position, delta E. And you would have the term that, right, that everyone knows about. So you have this 1/2 kx squared. But in fact, so that's when you move along this direction. But in fact, you have another term. And the other term is when you move along that direction here. If you move along that direction, you will change the length of this spring, if it's attached here, at second order. If you have a force in the system, you will have a change of energy that would go like the force times this change of distance. So it's also a quadratic term. You cannot neglect it with respect to that. Okay, so it's this very simple idea that if you move, you change orthogonally to a contact, you change the length at second order. If you have force in it, if you can think of this force doing some work, if you want. So for example, if the force is compressive, if the spring is compressed, the system likes to go along Y because you release some elastic energy in the spring, right? So you have two terms in the energy of a spring like that. One is positive, the other is negative if the force is compressive. In my notation, compressive force is positive F. If you think about those packings, and you are looking at this Hessian, the only terms that could be negative, that could lead to instabilities, is this term. So if you think about instabilities, saddle points, things like that, it can only come from those terms in a system like that. Yes?
So if you have a force in the spring, so you're not in the minimum of the potential. So
Right. So
shouldn't you have also linear term in X?
yes, I'm assuming that the system has an external force on it. Yes.
Ah, okay.
And then I look at the change of energy if I move.
Okay. So
Yes.
there is an external force.
There is an external force acting on it, yes. So this is this force F, yes, yes. Yeah, sorry. All right, then I think it's intuitive that if you think about packing, those two terms, coordination and pressure, are going to be important. And even I think Andrea gave you an argument we made a while ago, so I'm just going to give you the answer. But in terms of theory, so now that's the idea. Those two physical ingredients are going to play a role. How do you actually build a quantitative theory about elasticity, vibrational modes, and things like this? And in finite dimension, now there are new techniques in infinite dimension that maybe we'll hear about in this conference. We developed two ways to think about this. One is explicitly guessing what those soft elastic modes are. And really what it means, mathematically, it's a Varshon argument. It's because this Hessian matrix is positively definite. So just like in quantum mechanics, if for any state psi H psi has to be larger than the ground state, so you can bound the ground state energy with that. You can do the same kind of argument with vibrational spectrum in those disordered systems. And there's another path to it, and I think Eric will talk about this in the conference, which is treating the disorder perturbatively in a self-consistent way, and that's called effective medium. And probably you've heard of it, say, in the context of conductivity in a disordered network of resistors, for example. Here, you really understand physically what you're dealing with. Here, it's more a black box, but it's actually very powerful. For example, in terms of eigenvectors and length scale, it's the most direct way we have to extract what's going on. So if you do that, what you find is that you have a phase diagram for those packing of harmonic particles, for example. You have a phase diagram between pressure and coordination, a stability phase diagram, just an example of the marginal drawing I made, that separates an unstable from a stable region. So here, that's the coordination axis. If you didn't have any pressure, you would just find what Maxwell has told us, that the coordination needs to be larger than a threshold to be stable. And if it's too low, then it's unstable. But when you add pressure, as you may intuitively expect, it becomes more constraining to be stable. And so the coordination needs to compensate the destabilizing effect of pressure. And what you find is that you have a square root relationship between this coordination and this pressure. Okay, so you have a phase diagram like this. And here it's unstable, here it's stable. So again, I'm not going through the theory at all, but I think that was discussed, right? That was discussed in the previous talk. Yeah? Okay, so you can think about stability, but those techniques, they also give you much more. They give you, the density of state and some aspect of the eigenvectors. So here I'm just going to summarize what you can get. For example, so with those methods, you do get that you have this frequency scale like seen numerically when you approach this unjamming transition, when the packing has a lower and lower pressure. You find that the density of vibrational modes has to be flat above this characteristic frequency. But you can also access some properties of the eigenvectors. So remember, at jamming, this was completely flat, the density of vibrational modes. Now you can look at different frequencies and look at those eigenvectors, and you can define a correlation length for them by looking, for example, at displacement. And what the theory predicts is that this length scale goes like 1 over the square root of frequency. That's from effective medium. And I don't have a very simple argument to say that. But once you have that, you can intuitively understand several aspects of the problem. One is, since you have a characteristic frequency and a length scale for those modes at any frequency, you get a characteristic length scale. And that's the one that enters in those heterogeneities to the response of a point force. And you can also now understand why the diffusivity was flat. So the diffusivity is really a diffusion constant. So you can think of it as a length square times the frequency, right? So those modes, if you want, they are correlated. They have a characteristic time scale because they are the frequency omega, right? But they have a characteristic length scale on which they are correlated. So how much they transport heat will be related to the square of a length scale divided by a time scale or times the frequency. And then you understand why it's actually flat. All right. So that's actually what the statement I made here. So you know that for those packings have to be stable. The statement I made here are true everywhere in the stable part of this phase diagram. Because all those statements were actually made for frequency larger than this characteristic frequency omega star. If you look at smaller frequencies, what happened for very, very soft objects, then it matters where you are. Okay? And so that's the sampling problem. If you want, what is the relationship between pressure, so this should be P, between pressure and coordination? What is this relation Z of P? Okay, so what we realize is that if you look at the predictions and you look at those packings, what you find is that actually it's an observation where you live on those packing is at or very close to this marginal line. So it seems that those packing are on the edge, they live on the edge of an elastic instability. They just have enough contact to balance the destabilizing effect of pressure. This explains immediately two aspects. It explains the scaling relationship between coordination and pressure. But this scaling alone would not tell you that you live right here because you could be living right there or at the middle of it, for example. But most importantly, if you look at vibrational modes below this omega star, what you find in those packing is that even at frequencies much larger than when you reach the plateau, you have many more modes than what you would expect. And that can only happen if you're very close to this line. What you can prove too is that if you're right on this line, the sort of excess, you would have plane wave, but in addition to that, you would have other modes, and they would contribute to the density of vibrational modes in a quadratic way. So in 2D, it's just like the bi, but in 3D, for example, it's larger. That's independent of the spatial dimension. Okay, so now why is it marginally stable? So what we argued at the time with Tom Whitten was the following scenario. So imagine that you prepare your system, and imagine that you start in the stable part of the phase diagram. Okay? And we thought about a decompression. What we said is that consider the scenario where a decompression, so it could be more general, but we are thinking about that, that a decompression would change the coordination pressure, and so it would make you evolve in this phase diagram. Consider the case where this evolution leads you towards this instability, okay, towards this line. Then what happens when you hit this line? So what will happen is that some modes will become unstable. And physically, the reason is very similar to the buckling of a thin rod, right? So we're thinking about a zero temperature decompression. At some point, your metastable state is going to hit this line. When you do so, modes become unstable. Just like buckling, you would expect that this instability is will take place, but will not lead you to infinity. You will have nonlinear terms that actually stabilize you. So you have, when you reach that point, boom, you have those buckling events, and those buckling events would end up changing the pressure and the coordination in a way that avoid you entering in this system, clearly because this is unstable. You cannot stay here. So as you decompress further, then you cannot penetrate here, so you're going to actually follow this line, and the dynamics would be a succession of those buckling events. So that was our proposed explanation for why you live very close to this line. How close you live from it will be discussed by Eric, I think, in this conference. So this scenario was the recent result on that came from those authors. Many of them are actually in the room. And they could do exact calculation in infinite dimension. And what they could first show is that they found the same. Actually, it was not in infinite dimension for packing. It was a perceptron model where you have frozen disorder. But in subsystems, they could actually first show that the relationship between pressure and Z was the one predicted here. They could also compute the spectrum and have the same signature to the spectrum of marginalities that we had discussed, for example, this behavior. So it was, in terms of vibrational physics and linear physics, it seems to be completely consistent. What's very exciting about this result is that actually they also tell you something new. They tell you that when you reach this point, and you have this sort of sequence of buckling event, with this method, you can actually compute the statistics of the energy landscape. And what they found is that when you hit this line, actually the energy landscape becomes fractal. So this sort of succession of buckling event leads to a fractal energy landscape. And that gives you a new handle to think about nonlinear phenomena or two-step relaxation processes or things like that. And this is something I will not discuss because that will be discussed actually in this conference by various authors. Okay, so now let me, yes?
So I forgot to tell you, at some point, maybe we can make a 5 minutes break between the first.
Oh, really?
When you
Okay.
think it's a good moment.
Okay. Okay, so, all right, I can do this. Okay, so now I wanted to discuss the question of how do those ideas, that was for zero temperature packing of decompressed packing of particles, what do those ideas tell you for colloidal hard spheres? And in principle, they tell you nothing because for those hard spheres, you just have, the energy landscape is completely flat, strictly speaking, right? Because, or you have infinite walls, but there is nothing much a priori you could say. So what's the idea? To apply those kind of reasoning. So the idea is to do some kind of time averaging. So think of being in the glass phase here, for example. So particles are rattling around very rapidly, but the system cannot relax. The particles are not removing to long distance, to large distances, are not cannot diffuse away. One thing you can look at numerically is they rattle around, so they exchange actually momentum with each other. And so you can define a force between two particles that are close to an average force, a momentum divided, the total momentum divided by time gives you an average force. So if you average, you get something like that. So that's a 2D glassy system of disks. So you have disks, they were rattling around. They are rattling around those red positions. And you measure the force that they exchange. And what you find is that the sort of contact force network looks very similar than contact forces in packings of athermal soft particles above jamming. Okay? So that suggests that those ideas I just told you about are also going to be relevant here. So there are two quantities, two ideas that are important. One is that dynamically you can define again some kind of coordination. So previously for soft particles, it's at 0 temperature, it's obvious to define coordination. You just look who is in contact with whom. Here, what you can do is remember that the particles cannot diffuse away. So you have two time scales essentially. One vibrational time scale, which is fast, and a very long time scale, which is the time where they can diffuse away. If you take a time scale in between, you can define a measure of coordination, because you can decide which particles have touched each other. That defines the contact. Once you define contact, well, you just have to look at this contact force network and measure its coordination, right? So you can define coordination. That's one thing. The second thing is, if you want to think about the stability of that, you need to have some kind of energy functional and compute the Hessian. And here again, the idea is averaging. Instead of looking at the energy, you're going to look at some local free energy. What you get, and which actually becomes exact at very large pressure, is that two particles that are bumping into each other, once you average, they interact with the logarithmic potential. Here, h is just the gap between them. This result, actually, you can do a simple calculation. Think about a one-dimensional system. You put two particles, you put forces on it at some temperature T, and you compute the force versus average distance relationship. You would just get kBt over h, as you expect if you take the derivative of that. So I'm not going to redo this derivation. I will just take it as granted. So then what you get is a coarse-grained free energy, which is just the sum of all the contacts of this kBt log Hij. All right? Again, if you want to think about this very simply, it's just log H is just the entropy of this 1 degree of freedom, right? I mean, it's how much phase space there is in this contact. So for hard fields, there is just entropy, so that's why you just get kBt log H. Yes?
So how do you define the effective coordination for Brownian dynamics?
But it's the same. You could just look in a code. You could just look who is.
Never collide, really?
Well, you could still define when they kiss each other, right? For a numerical. You mean in terms of numerical procedure? So this result is true for, it's a theoretical result, which is actually thermodynamics. So what you're asking is more a question of how would I.
Effective coordination.
Right. Well, I think you could define it in the same way, right? If you have two particles and they are Brownian, you can just put a cutoff and say when they are close enough to each other. Right? You just look. It's the distance between two particles is doing a random walk. You look at when it crosses 0. So if it does cross 0 at times, then you declare that they're in contact. Okay, then once you have defined this effective potential, you can just use the same machinery, right? You can think about this free energy. You can think about its Hessian that is going to and the eigenvectors of this Hessian are going to describe the sort of curvature of the free energy. And what they will characterize are the collective fluctuation of your hard particles. If you have modes where the free energy is very flat, it means that you will have a lot of displacement along those directions. All right. Okay, so now theoretically, if you want to think about this free energy, you can again analyze it with effective medium or variational argument. And again, here I'm just going to give the answer. You get a phase diagram which is very similar to quantitatively slightly different, but overall very similar to what I told you about, where you have an unstable and a stable region. When you're right at jamming, it's the same criterion ZC. If you now lower the pressure, if you go more dilute, then you must make more contact again to be stable. So you again have a phase diagram of this type. And again, if you can so compute vibrational properties that describe the microscopic dynamics for any of those stable configuration. And again, what you find support that actually you will live right on this line here. And the consequence of living right on this line would be those scaling laws for the frequency scale, for the length scale, and for the density of vibrational modes. So so you have non-trivial exponents here, so you can ask how convincing is it numerically? Well, I think, for example, this quantity here, the fact that for hard spheres the density of vibrational mode is not flat like for soft sphere, but slightly tilted, is actually qualitatively observed in numerics, for example. So I think those things are actually true. Okay, I just have 2 slides before I break. I think it would be a good time. So right, and you can also look at this coordination versus pressure relationship. So what it's supporting is that those colloidal hard spheres, so those systems that are bouncing into each other, live again close to the edge of an elastic instability. This effective free energy has direction in phase space that are almost completely flat. Okay. All right. So now let me just briefly mention how this. And then I will come back as to why it's like that. But first, let me also comment on another idea which I think is interesting. It has to do with now the glass transition. How do you enter in this glass phase? So there has been a popular idea, I think initially proposed by Goldstein, but also very popular for mean field approach to glasses, is the fact that the glass transition has to do with the sort of transition between a high temperature or low packing fraction regime where the free energy you leave close to saddles, you always have unstable direction in phase space, and then at low enough temperature, or here in this context at large enough packing fraction, you suddenly have states that are metastable, and the dynamics becomes activated. So that has been a popular idea, but one question is, so essentially you had saddles, and then suddenly you have minimum. So you had directions in phase space that were unstable that became stable. And one question is, what are those directions exactly? So the fact that those hard sphere glasses are marginal to those anomalous modes actually support that those modes that control this exchange of stability are precisely those objects we're talking about. And that the onset of the glass transition takes place when, so let's say you increase the density, so you would increase the pressure. So in this phase diagram, you would be doing something like that. And the glass transition would take place when in the vicinity of the point where you actually enter in the stable phase. So you enter here, and then suddenly the dynamic changes. Instead of flowing along a stable direction, it becomes activated. You can still penetrate in this regime, but the dynamic has qualitatively changed. So what I was telling you about give you this effective medium approach and so on may give you a handle on what are those objects whose stability is actually exchanged. Okay, so this is the last slide I want to comment before I take the break. So here again, you could ask, why is it that this colloidal glass is really marginally stable? And the result of Charbonneau and co-workers, Francesco, Parisi, and so on, support the following scenario in this phase diagram. So that's the equilibrium curve. So as you increase the pressure, as you increase the pressure, at some point you would hit that curve, mode would become stable, and the dynamic would become activated. You can still equilibrate the system because those barriers have a finite height, but at some point you become unstable. Okay? this point where you become unstable would depend on your quenching rate. So if you quench rapidly, it would be here. If you quench slowly, it would be here. When you become unstable, then you can think of being stuck in one metastable state. But then you compress further, and you adiabatically follow this state. What the results support is that, at least in infinite dimension, is that once you do that, in this phase diagram, when you compress further, you're again driven towards this elastic instability. So now you live in a well-defined metastable state, and you go toward an elastic instability, and then again you will have this buckling dynamics I described in the previous slides, which in their formalism leads to this Gardner transition and fractal description of energy landscape. And again, from their approach, that would lead to to interesting nonlinear properties and complex relaxation function. This I'm not going to enter again because you will hear about it in this conference. Okay, so I'm going to stop here for 5 minutes, and then I will talk about more discrete excitation. But I can take questions. Is there